So here you can see in this application there's a CSRF vulnerability. CSRF stands for cross-site request forgery. This is type of an attack in which a malicious third party takes advantage of a user's authenticated credentials, such as a browser cookie, to act like that user and perform unauthorized actions. So as you can see here, there is no development framework is used which defend against CSRF attacks, and no unique hidden tokens are checked by the server to validate state change requests. So if I move here, you can see we used CSRF protection, CSRF middleware to prevent this. CSRF middleware generates a unique hidden token, and that token is sent via this endpoint to the client side. And from client side, that this token is stored inside cookies. And from this Axios instance, as you can see, we get that token which is stored inside the cookies, and along with every state changing request we send that cookie again inside request headers. So this is called double submit cookie pattern. With this we can prevent CSRF attacks. And if I move here again, you can see there's another vulnerability called open redirect. Open redirect attacks takes place when a web application redirects the user to an unauthorized and untrusted site. This can be done through social engineering, tricking the user into believing they are accessing one site when in reality they are being redirected to a dangerous sites such as phishing site. So here, as you can see, there is no input sanitization or input validation is used to prevent this open redirect attack. But here, as you can see, we have used input sanitization and input validation to prevent open redirect attacks.
Welcome to this detailed list of not too critical security vulnerabilities that we encountered and fixed in our repository for cybersecurity and partners. I will walk through where we found these vulnerabilities and how they work and the approaches we took to secure this repository. First of all, I will talk about the cross-site scripting. As you can see here, we could found two places where this XSS attack can be occurred in this repository. First, I will go to this tutorial controller. Normally, it occurs when an attacker uses malicious scripts, typically JavaScript in the web pages viewed by other users. The injection script can then run in the user's browser, stealing sensitive information like cookies, sessions, programs, or performing actions on behalf of the user without their consent. So, in this repository, as I mentioned before, we found two places in this place. Using inputs were not being sanitized properly before the rendering back into the web page. This means that an attacker would inject a malicious script into the input page, which would be then executed in the victim's browser when they view the content. Like in here, like they have used so many unsanitized user inputs. To mitigate this vulnerability, we implemented input sanitization across the application. Specifically, we use the XSS library in this tutorial control.js file, which helped us to clean these inputs before they were rendered in an environment. The XSS function strips away any dangerous elements or attributes from the user inputs and ensuring that no harmful scripts make it to process. As for the second encounter, in this we use a KSX file, the application dynamically generates HTML using unsigned as user inputs. As you can see, here they use these class names and without any sanitization. So this might open up the possibility for a DOM-based access attack. In DOM-based access attack, malicious scripts are inserted directly into the client side code that can execute within the context of the user browser. DOM-based access is vulnerability. In this page, we integrated the DOM purify library. This library sanitizes any dynamic content that user inputs before injecting into HTML document. DOM purify automatically removes malicious scripts, preventing attackers from using harmful content in the page. Okay, next I'll talk about this path traversal attack. This is another critical vulnerability we found in this repository. Path traversal attack occurs when an attacker manipulates file paths to access directories or files outside the internal directory structure, potentially exposing sensitive information like server configurations or source codes. So in this repository, this vulnerability was found in this compile controller JS file, where unsensitive user inputs were passed into the write file sync function. Since write file sync function writes data into files, attackers could exploit these unsigned files path to perform a path traversal attack. First, we limited the characters allowed in file names only to alphanumeric characters and underscores. We enforced this using regular expressions, ensuring that input could not contain any special characters or sequences like dot slash. The attackers could use to navigate outside the intended directories. Furthermore, we used path.base name, a built-in Node.js method to ensure that the file path was safely constructed without any risk of directory traversal.
We can see that there is command injection vulnerability in this code. This vulnerability allows attackers to execute harmful system commands through the application. In this section, both Java compilation and execution were done in a single command line. The problem with this is that file path and class name come from user input, which could be tempered with if an attacker inject something malicious command like add-in rm hyphen rf slash to the class name, they could run destructive system commands. To prevent this command injection, we need to split the Java compilation and execution into two separate steps, and instead of using exec, we use exec file which passes arguments directly without invoking a cell, and also user input is sanitized by this function before passing it to the exec file function. By doing those, we eliminate the risks of the cell interpreting user input as part of a command. This makes the code much safer because it prevents an attacker from injecting malicious command into the execution. There is a REDOS vulnerability. REDOS stands for regular expression denial of service. This type of vulnerability occurs when an attacker can exploit inefficient regular expressions. This could lead to the server becoming unresponsive, which is called a denial of service attack. In this search function of application, use the regular expression to match a user's query. The issue here is that the key query which comes from the user is passed directly into the regular expression constructor. This allows a malicious user to input something complex and exploit the engine's backtracking behavior, slowing down the server and potentially crashing it. To fix this issue, we need to sanitize the inputs before using it in the regular expression. This is the fix code. By adding this line, any non-alphanumeric characters are replaced, ensuring that only safe input goes into the regular expression. And also this part, check to make sure key query is a string, which avoids unexpected input like objects or arrays that could cause errors. After fix this, the regular expression can't be manipulated into slowing down the system.
Screenshot that's relevant to the prototype collection vulnerability. So mainly, prototype collection is a vulnerability that allows an attacker to modify the object of prototype or any base prototype of JavaScript objects. So as shown in this, the update exercise answering sections of the results are containing array index manipulation. This could be vulnerable when a user is overriding the properties of the JavaScript objects. So in here, you could see that the function has been updated. Value that's been coming to the relevant index is being conditionally changed, whether it's an object, proto, or constructor. The next part, allocation of resource without limits. In here, the code compiler takes unlimited amount of code length, with limiting the code length to 1,000 characters. Also, as shown, I have implemented an express rate limiter, which limits the resource consumption that is being done by a specific user under a specific IP address. What allocation of resource without limits vulnerability specifies is it's a condition whereby some of the resources of the server, such as memory, CPU, or disk spaces, are dispatched to perform certain tasks without controls that are adequate. So this thing is being handled here as a part. Maximum of 100 kilobyte of limit added as a barrier for the incoming request payload. So the next part, brute force prevention mechanism. In here, we have implemented a brute force limiter with some specific configurations and that is being used as a middleware where the main authentication endpoints are relying. The next part, cross-config handling policies. So I had included these set of codes which specifically figure out which clients are getting connected to the server resources. According to this code, these two URLs are allowed as API testing tools like Postman's tools can also be allowed in the server resource.